So today we are going to be graphing reciprocal functions, and in 8.3 we're talking about a very specific type of function. Okay, in general, this is what reciprocal functions look like. Okay. F of x or y equals 1 or some constant over a linear function. A of x has to be linear, and it can't equal 0. A linear function, remember, is just x to the first power degree 1. We can't have, for reciprocal functions, we can't have any degree other than 1 in the bottom. This number is going to change sometimes from 1, but it'll always be a constant. And I'm going to show you another form of it later. But for today, for our assignments in 8.3, all of our equations are going to come in the form like this, where it's like a constant over a linear function. When we get to 8.4, we're going to be looking at some other rational functions where we can have fractions, all kinds of fractions, and all kinds of different powers in the numerator or denominator, but today we're going to keep it pretty simple. All right, so what we're going to do is we're just going to look at one example, okay? And we're going to talk about the parent function. And back when we did transformations in Chapter 2, we talked about absolute value parent functions. We talked about quadratic parent functions. We talked about linear parent functions. Well, we're going to talk today about linear or parent functions that are reciprocal functions. So remember that the parent function is the most basic, boring, quote-unquote, model of that particular type of equation. And so then we'll do things to it, add things to it, subtract things to it, multiply by it, put negatives in, make them flip, make them slide, make them shift, make them stretch, make them compress. So we did all that in Chapter 2. We're going to do the same kind of thing here. Now what I want you to do right now is in your calculator, I want you to enter this equation, go to the y equals screen, and enter this equation, and then graph it in the standard viewing window. So remember, that's Zoom 6. Go ahead and enter that and then take a look, and you're going to get a funky looking shape. If possible, if your calculator gives you the ability to put these things in as a fraction, I recommend doing it that way. Some of your calculators are too old and won't let you, and you have to put it in as a division problem. And when we get to some other problems later, I'm going to show you another way to enter them so you don't have an issue. Again, to get to that standard 10 by 10 window, Zoom 6 is where you want to go. Zoom 6, okay? So hopefully, is anybody having trouble getting that entered in? So here's your graph should have looked like. It should have looked like something like that, okay? And the thing that's important to understand about the parent function of a reciprocal function, just like when we talked about exponential functions, this graph never touches the y-axis. It'll get close. This part of the graph will never touch the x-axis. It will get close. Same with down here. It won't touch the y. It won't touch the x. They're kind of mirror images of each other. Okay. This shape actually has a name. And so when we... No, that is not the name of the shape. The name of this shape is a hyperbola. Okay. This is what a hyperbola looks like. It has that mirroring image where it will border a vertical line and a horizontal line. In this case, the x and y axis. It's like we don't say parabola, we say parabola. Same thing here. We don't say hyperbola, it's a hyperbola. Okay, and so a new shape today. We're going to talk about domain and range, and I'm going to put this up here, and then this will be the last time we talk about domain and range this way, because we're going to talk about it in a different way, and I'll show you the way I would prefer that you do it. And to me, that's an easier way. In this case, if we look at this graph, we're trying to determine the domain and range. Okay, so if I'm looking at domain, I'm looking at my x values. Obviously, this goes on forever, gets bigger and bigger forever. And this way, it gets smaller and smaller forever. The only value for x that it can't be, that doesn't ever touch the graph, is where x equals 0. It's everything else but where x equals 0 for the domain. And the same thing is true for the range. It goes up forever. It goes down forever. The one place that y never is when it's 0. Okay? And so the domain and range, the way the book expresses it, is all non-zero real numbers. Anything but 0. Okay, x can't be 0, y can't be 0. Or in this case, f of x can't be 0. Like I said, as we move our way down this table, this little chart, I'm going to show you at the end another way to express domain and range that I want you to use from this point forward. This will be the last time we write it this way, because it's easier to do it the way I'm going to show you. Now, the next thing is going to be something new, a new term, and it's called an asymptote. An asymptote, just so you know, is a line that basically creates a boundary. And we've talked about ceilings and floors and walls before. That's what an asymptote is in this problem. The difference is our ceilings and floors and walls were always on the outsides of the graphs, above the graph, below the graph, to the right and left of the graph. Asymptotes are boundaries that occur inside the graph. Okay, and in this case, we have two asymptotes. It never touches the y-axis. That serves as a boundary. It also never touches the x-axis. Well, the equations for those lines are the asymptotes, and I drew them in. So in red, in this red highlighting, I have the y-axis. The y-axis is the equation x equals 0, because all the values on this line for x equals 0, the y values keep changing, but the x value is always 0. That's why this is a vertical line. This is what's known as a vertical asymptote. Okay, and when you work through your homework today, if you want to label it V period, A period, that's fine, to indicate that you're telling me about the vertical asymptote. The x-axis, where the y coordinates are all 0, is the equation f of x equals 0, or y equals 0. Again, this is the horizontal asymptote, and in your homework you can abbreviate saying H period, A period, so that we know it's the horizontal asymptote. I am going to ask you to distinguish between the vertical and the horizontal asymptote, okay? Don't just tell me what the asymptote is, tell me which one it is. I'm going to be particular about that. I understand that some of the things that I'm going to show you here in a second that the book does, I don't think they don't put it, they just say the asymptote. I want us to really reinforce the idea of which one's vertical, which one's horizontal, because I want to reinforce the idea of what those equations need to look like, all right? So the asymptote is something that's actually not a part of the graph, right? The asymptote are the places that are boundaries, that the graph never touches. And so when we indicate what the asymptotes are, we're saying this is a boundary. The graph will never touch this line. Okay? That's what an asymptote really is. One of the things to keep in mind for vertical asymptotes that's really important, in case you can't see the graph, the way to tell where a vertical asymptote is going to be is fairly simple. It's going to occur at every x value that makes the denominator of the equation equal to 0. Let's dive into that a little bit more and try to make some sense of that. If this denominator was 0, we would have 1 divided by 0. What do we call that when you divide by 0?
Can't have it.
You can't have that. We have a term that we use, though. Undefined, thank you. Okay, it is undefined. It has no meaning. It has no definition, right? How do you divide into groups of 0? That's what division is. You divide it into a certain number of groups. You can't divide something into groups of 0. That doesn't mean anything to us. We try to think about it and try to visualize it. We just can't, because it doesn't make sense. So a vertical asymptote is specifically when the denominator equals 0. Meaning those places can never be a part of the graph because they have no meaning, they are undefined. So if you're unsure of where to find the vertical asymptotes, just look at the equation and go, all right, what values are going to make the denominator 0? In this case, it's just 0. So that's why x equals 0 is an asymptote. All those things are connected. That's an important concept, and we're going to keep working through that. All right. One of the things that sometimes they'll ask is about the intercepts. What are the x and y intercepts for this particular graph? Nothing. They don't cross the x and y axis. Sometimes they'll ask you about that. So there are no intercepts. When we shift the parent function around, it'll cross the x and y axis sometimes. And it might ask you for those things. Okay. And then the last thing before we kind of wrap this one up and talk about how to rewrite the domain and range is, again, going to this concept of undefined. Okay, what values make the function undefined? Simply stated, whatever makes the denominator equal to 0 will make the function undefined. Okay, so we just want to be sure that we understand what that means, undefined. If the denominator equals 0, it's going to be undefined. I know it feels like I'm beating that point to death, but it's an important point. And I want to make sure that you remember it. All right. The last thing I want to do before we move on to another type of problem is talk about how to rewrite the domain and range in a different way. Since we've decided and we agree that the domain, that x can be anything but 0, and y can be anything but 0, in this case f of x can be anything but 0, it's better if we write it in that way. And so what we're going to do is from now on, we're going to write the domain range this way. Instead of saying all non-zero numbers, let's just say x can't equal 0. That implies it can equal everything else. And we're going to say that the range f of x can't equal 0. It can equal everything else. It is not a coincidence that the domain and the asymptote look very similar. It is not a coincidence that the horizontal asymptote and the range look very similar. That will always happen. Because again, keep in mind what an asymptote is. It's the boundary. It's the place that the graph doesn't actually touch. So those are the places where we exclude them, those values, from the function. And that's what this domain is doing. We're excluding 0. The asymptote is saying, don't touch the line x equals 0, because it's not on the graph. Same thing here. We're excluding 0 from the y's. And that's what this is saying. Don't touch this line y equals 0, because the graph's never going to touch it. So you just got to throw that value out. Okay, that's how the asymptotes and the domain and range are related, and they will always be related like that. Okay, questions about anything we've done so far? All right, let's move on to another kind of problem that you're going to see in your homework. The first two problems in your homework today are going to be graphs that they give to you. So when I put this on the screen, go ahead and take a picture of it, and then we'll work through the problem together. Here's what I want you to do first. I want you to, on this graph, because we need to find the asymptotes and then the domain and range, okay? What I want you to do in some other color, you can use a highlighter if you want, it's whatever. I want you to draw the asymptotes in where you think they should be. Okay, you know how I drew them in red and green on the last picture? I want you to draw them in where you think they should be, and I'm going to come around and look and see if you put them in the right place. In the book, a lot of times they put the asymptotes in using dotted lines. So when you see dotted lines, you can use that. You can use a highlighter if you want. You can use a just different color. I don't care. And I understand that when you draw them in, they're probably going to hit your graph a little bit, but we know that they really never touch it. So as we work through this a little bit more, it's going to be easier to see where that vertical and that horizontal line need to go. Now, after you draw them in, okay, hopefully you had something like this, which, walking around you had, I could see. Now we have to actually say what the asymptotes are. All right, so let's start with the red one, the vertical one. What is the equation for this line right here? Just say it out loud. X equals negative 2. X equals negative 2. Again, let's go back to this idea of undefined. Does negative 2 make this denominator equal to 0?
Yes.
It does. Okay, so that reinforces what we've drawn. That yes, negative 2 will make this 0, which will make it undefined. Therefore, the vertical asymptote is the line x equals negative 2. So that's good. All right. The horizontal axis, or asymptote, is going to be what? Y equals negative 1 if there was a y in this problem.
G of x.
G of x. Okay? G of x equals negative 1. That is my horizontal asymptote. Okay? And again, you could write, if you wanted to, instead of writing it all out, you could write VA and you could write HA. I just want you to identify the horizontal and the vertical, please. Okay? So we've done the asymptotes. Now we got to find the domain and the range. Okay? Remember that the domain is very much related to which one? The vertical or the horizontal?
Domain.
The vertical, right? The one that has x in it. So what this is saying is that the graph can't touch this. So what it's telling you is the graph, the function, can be any value but this. So my domain is just going to be x not equal to negative 2. All right. X can be anything except for where the asymptote is, negative 2. And so the y, or the g of x in this problem, the range, can be anything but negative 1. So my range and just being g of x not equal to negative 1. Okay. Now, here's where we really want to put it all together. You should be able to determine the asymptotes and the domain and range without actually looking at the graph. Okay? And if we think back to our transformations and what we did in chapter 2, and that whole inside with the x versus outside, that's where we look to find our numbers. Okay? So these numbers, for that matter, those numbers all go together, right? In our formula, the -1, which is outside, so that affects up or down movement, which affects the y. This -1 shows up with the g of x in the horizontal asymptote, shows up with the g of x in the range. Inside, so this is inside a fraction, we go opposite sign, plus this is what makes the denominator equal 0. That's why it's negative. So I got my negative 2 with the vertical asymptote. I got my negative 2 with the domain. You can pick all of that information off from the formula. So, for example, if you're having trouble seeing this, the asymptotes, the vertical and horizontal asymptotes, you can look at the formula, look at the equation, the function, and go, okay, wait a minute. I know there's a relationship between this and this and this. Okay, so you can tie that all together. You'll have a couple problems like that. Okay, questions on that? All right, the ones that will take you the most time, and before we get there, sorry. This is just a general rule. You can take a picture of this screen if you want. There's a lot of information on this next screen, but it's really talking about the transformations and reinforcing this idea that inside with the x is a left and right shift. Outside of the x is a vertical shift up and down. And then if I multiply this by something, it's going to stretch it vertically or compress it vertically, Or it might flip it to a reflection. We talked about all those kinds of transformations back in chapter 2. And on this next screen that you can take a picture of, basically is just explaining all of that. Okay. I wrote it in a little bit different form so that it always looks like the reciprocal function form with the 1 on top, sliding the A out. So that's how you can see that it's still reciprocal function form. This A is a scalar. It's a dilation. But this is the general form for a reciprocal function. And after you get that in, I'll talk more about all of this transformation stuff. Here's what all this is trying to say, right? This inside move, opposite direction, right or left. Okay, so horizontal translation, meaning it moves right or left. This on the outside is an up and down, vertical translation, a slide up and down. This A, the multiplier, means it's either going to get stretched vertically or compressed vertically. And then if it happens to be negative, the thing's going to flip. All right, all of those transformations we talked about way back in chapter 2. That's all that this is trying to say. Okay? So what we're thinking about is that original parent function 1 over x, and then changing it by multiplying stuff by it, adding or subtracting things to it, adding, subtracting things inside the denominator, and you'll get a variation of other reciprocal functions. Now, in your homework today, you're going to have problems like this. It's going to say graph each function, state the domain and range. Now, I'm going to add some instructions today that are also going to say identify the asymptotes. Okay. And I'm also going to have you list points because you're going to actually graph. Now, after we go through this presentation, I'll show you the actual directions that I've added in Canvas that basically state all of this. So the first thing that we're going to do is figure out what the numbers in the equation mean for us, okay, and what they do, because we can find the asymptotes, we can find the domain and range without graphing. So let's do that. Let's start with the asymptotes. Let's start with the vertical asymptote. Okay, we're talking about x. What value of x is going to make the denominator equal to 0? Undefined. Negative 1. So the vertical asymptote is x equals negative 1. I want to get rid of this. I don't like that. Which means what other thing do we know right away? Well, yes, but if I know this, what can I immediately write? Yeah, the domain, right? The domain is what? X does not equal negative 1. Okay? All right, now, Jill, give me the horizontal asymptote.
4.
Give me more information. Yes, that number is correct. That's so warm, but not quite right. F of x equals negative 4. So then, right away, what do we know?
Range.
We know the range. Okay, so the range is f of x cannot equal negative 4. All right, now let's talk about the graph itself. So when you enter this in your calculator, ideally, because that's what we're doing now, okay? Ideally, you enter it in just like it's written. But if you have an older calculator, you're going to have to be careful. If you have an older calculator and you need to type it in as a division problem, here's what I want you to be careful of. Make sure that you put the denominator in its own separate set of parentheses. If you don't include these parentheses here, if you have to enter it as division, or if you just choose to enter it in as division, you're going to get a different graph and a wrong equation. Okay? So go ahead and enter that in your graphing calculator, and then we'll show you what to do from there. again, this is the preferable way to enter it. If you can put a fraction on your y equals screen, I know some of you can't do that. And so just be careful. You want to make sure that you put all of that denominator in its own set of parentheses. I mean, for that matter, if you wanted to, I mean, this is overkill, but if you wanted to put all of this in its own set of parentheses, you could. You don't have to, though. Okay? Now, the one thing that this negative here flips it. So you notice how we had upper right was a graph and lower left was a graph. Now it should flip. And so I should have upper left a graph and lower right a graph. And hopefully that happened for you. Now, when we've done pretty much everything. We got to graph it, though. All right? And in order to graph it, we need the points. So we've done all this already. And again, this is... This is the vertical asymptote. This is the horizontal asymptote. And we found the domain and range already too. But the graph, when we go to actually put the graph in, it's going to look something like this. I want you to list points. Now I want to talk to you a little bit about where to look in your table to find the points. I want to make sure that we're all clear about where that is. All right, so I'm going to add a little picture in here. So if you go to the table, your table looks something like this. Okay. Let's just leave that there. Okay. Your table looks something like this. And I happen to scroll to a particular place. And that place is right here, this -1, and then it says error. What does this line represent?
0.
Yeah, where it's undefined, where what occurs?
0 in the denominator.
0 in the denominator. What else occurs on the graph?
No, the asymptote.
The vertical asymptote is right here. Okay? So what this tells me is that these points are to the left of the asymptote. These points are to the right. So when I'm telling you to list points in your homework today, I mean, I would say -4, -3, and that's where I plot it. I got a point there. And then I'm going to write down -2, -1. You're going to write these points down in your homework today. And you're going to graph them. And then you're going to have some other points on the other side of the asymptote. 0, -7. And then I've also got 2, -5. Now, if they don't turn out to be nice values, or you have something like this where it's writing it as a fraction, just change it, Make it -5.5 and graph it that way. I want you to graph at least 2 points for each portion of the hyperbola, okay? And write down 2 points. In your table, you can always find where the asymptote is whenever it gives you an error. That means it's undefined there. That's why if you plug -1 in to x in our equation, that makes the denominator equal to 0, makes the calculator tell you it's an error, which is undefined. Okay? Questions on any of that?